All right, so let's continue with the last video. So last video we talked about to make the hypothesis test about the slope beta 1, right? So that we can test whether the regression is significant or not significant. There is significant linear relationship between x and y or not significant linear relationship between x, y, right? So except the assumptions we have already done with all the 4 steps, right? So for today's video, first we'll talk about the assumptions. So for testing about the regression, we will have 4 assumptions, right? So it will be these 4 assumptions. All right, so let's talk about each assumption individually. Right, so the first one, we need to check the linearity. So we call it is the linearity assumption. So how to check the linearity assumption? We can go to look at the scatter plot, right? So from the scatter plot, we say the scatter plot is the easiest way to find or show the relationship between x and y, right? So from the scatter plot, at least there should have some linear relationship. You don't know whether it is significant linear relationship or not. That's why we need to test about it. But at least you should see the linear relationship, right? So for the linearity assumption, you need to go to the scatter plot to check the scatter plot to see whether there is any linear relationship between x, y. We do not want the curved relationship. All right, so I think it's kind of misleading. So let's say, just say no curved relationship. All right, so that's done, right? So for the linearity assumption, you need to check whether x, y are linearly related. So you need to check the scatter plot to see whether there is a curved relationship instead of the linear relationship. All right, so let's check the second assumption. It is called the independence assumption. So this one will be the easiest way to check the independence. We just think about it, right? Think about whether the observations in the sample are independent of each other. So normally, if the sample is randomly selected, then this independence assumption will be checked. All right, okay, so this is the independence assumption. Next assumption is called the equivariance assumption. For equivariance assumption, we want to check whether the points are equally spread out. All right, so what does that mean? So look at this scatter plot, right? So are the points are equally spread out? No, right? So we see that the points are grouping kind of 2 different groups, right? They have the clumping, right? So for this case, the equivariance assumption is not satisfied. All right, okay, so we can look at the scatter plot to see whether there is any clumping. So we expect no clumping, right? Sometimes it is not easy to find these whether it belongs to a clumping or not. So we will use another plot, which is called, let's say this way. Then we can check the residual plot. All right, so what is the residual plot? Let's look at this plot, right? So this plot is the residual plot. We say we plot the residual. Still remember what is residual? Residual is obtained by y minus y hat, right? So it will be the observed value of y minus the predicted value of y, right? Okay, so the residual versus the predicted value of y, we call this scatter plot, right? So we make the plot with residual and the predicted value of y. So we have the predicted value, and then y-axis will be the residual, right? So for this kind of plot, we call it is residual plot. Sometimes you may also see some residual plot is the residuals versus the x values, also called the residual plot. So it doesn't matter which one you use, either one is called, both of these two are called the residual plot. All right, so we say you can check the scatter plot to see whether there is any clumping, or you can go to you can get the residual plot, and then we say we do not want this shape. So we call this shape is the fan shape. And also we do not want another kind of the shape. So for example, if I draw the residual plot and 0 here, right? And then we have the points, something like that, right? So for this case, the residuals are plotted like a cone, right? So we do not want either one. We do not want to see a fan shape. We do not want to see the cone shape, right? So here, for these two cases, will be the equivariance assumption is not satisfied. It's not checked, right? So for the third assumption, we can check the scatter plot to see whether there is any clumping, or we can check the residual plot to see whether there is a fan shape or cone shape. For this two, that means this assumption is not checked. All right, so what kind of residual plot is good, right? So we see the two of them are not good ones. We say we want the residuals are equally spread out, maybe not exactly equally spread out, right? So kind of equally spread out about the 0 line, right? So for this case, good. For these two cases, not good. All right, okay, so this is the third equivariance assumption. The last assumption, we call it is the normal population assumption. So do we check whether the population is normally distributed or not? No, this is not the one we want to check. We want to check whether the residuals are normally distributed. All right, so to check the residuals, you can either check the histogram of the residuals, or we can check another plot. We call it is normal quantile plot. Either histogram of the residuals or the normal quantile plot. All right, so let's look at the details. So for this assumption, you can we will have this kind of plot, right? So this is called normal contour plot. And then the left side is the histogram of the residuals, right? So for this case, if you have this histogram, it is not normally distributed. It is not symmetric, right? And also from the normal contour plot, we expecting the points, the black points, follow a straight line like this, right? So for this case, you have the outliers here in then these points are not strictly followed, right? So for this case, it is still not satisfied. All right, so we expect a straight line for the normal contour plot, or we can check the histogram to see whether the residuals follow the normal distribution. All right, so here we'll talk about how to generate these plots, right? It will be easy. So it's the same thing. You can go to the analyze, fit y by x, right? So the price is x, the sale is y, right? Then click OK, and then first you will have this scatter plot. So we can use the scatter plot to check the first assumption, linearity assumption, right? So it shows some linear relationship, right? So first, this linearity assumption is checked. And then since these 52 stores are randomly selected, right? So we say the independence assumption is also checked. The next assumption will be the equivariance assumption, right? So you have two options. The first option is you can still look at this scatter plot to see whether there is any clumping, right? So for here, you have the clumping, one group, the other group, right? Or you can do fit the line, all right? And then based on this line, we can calculate the residuals, right? And here you don't need to calculate by yourself. If you clicked this red triangle here, you will find these many options to show you. All right, so here you will have this option, which is plot residuals. All right, so let's click that. You will see 5 plots for different residuals. All right, so let's look at each one. The first one is called the residual by the predicted plot, right? So we say x-axis, the horizontal x is the predicted y, and then the vertical axis is the residual, right? So this is the residual versus the predicted y. We call it is residual plot, right? Okay, so this is the one we look for. All right, so this is the residual plot. What about the next one? The next one is actual by the predicted plot. So that means this is the predicted value, which is y hat. This is the actual value, which is just a y, which is the observed value, right? So we have the y hat versus the y. That means this is not the one we look for, right? We look for the residual plot. This is the residual versus the row number, so it's still not the one we look for. So this is the residual versus the x, right? So remember what I said about the residual plot, right? So we say either the residual versus the predicted y or the residual versus x. Both of these two are all called the residual plot, right? Okay, so let's look at these two plots. These exactly kind of the same thing, right? So it's kind of just the reversed version of this residual plot. So you can just choose either one. So for me, I usually choose just the predict y versus the residual. All right, and then based on this residual plot, we can check the equivariance assumption, right? So we see the same format. We have the fan shape, right? So it's getting wider and wider for the residuals, right? So the equivariance assumption is not checked. All right, so the last assumption will be normality assumption, right? So we need the histogram of the residual or the normal contour plot. So the histogram of the residuals will be this histogram, right? So we see is the same plot as what we get in here, right? So we have this histogram of the residuals. It shows not symmetric, right? So it is not normally distributed. And also by the normal contour plot, the points are curved. They are not follow this straight line, right? So for this case, the normality assumption also not checked. All right, so is that easy? We just have three plots will be quite enough to check these assumptions, right? So we need again, let's say this, okay, we say we need the scatter plot to show whether there is linear relationship between the for the linearity assumption. We need to think about their independence. And then we need the residual plot to show whether there is any fan shape or cone shape, right? We do not want to see that. If you see this shape, then this assumption will not be checked, right? And then the last one, for the normality assumption, you use the histogram or the normal contour plot. So normally this is preferred, the residual plot is preferred in scatter plot. Right, so normally we use these three plots will be enough for these four assumptions. All right, so for this case, right, for our example, right, so we say out of these four assumptions, the equivariance and normal population assumption, these two assumptions are not checked. Do we just stop testing it? Actually, what we did is not, right? So even though the assumptions are not all of them are satisfied, we can still make the test, right? So this is the major difference between what we did before and for the regression. Because for regression, we do not have these perfect situation. All right, okay. So what we do, we will keep these assumptions. We say the linear assumption checked, independence checked, the equivariance assumption not checked, the normal is not checked. Then just stay there. All right, and then we can keep testing for other things, whatever you want to test, and then we are trying to find a better regression. If you cannot find a better regression, then this regression will be the best one, even though the assumptions are not checked. The other way, that means if you can find any other regression based on this sample, a better regression which satisfy these assumptions, that means that model or that regression is better than the one we have right now, and then you can just use the new model instead of this old one. So actually these assumptions are used to compare the models. You cannot just stop testing just because the assumptions are not satisfied. All right, so this is the main difference between what we have learned before and for the regression. All right, so here I just make a summary of the assumptions on the conditions, right? So first you make a scatter plot to check the linearity, and then you fit the regression and find the residuals, predict the values, so you even don't need to find them, right? So you can ask jump to plot the residuals and the predicted value y, right? And then you can think about the independence assumption and make the residual plot to see whether there is a fan shape or cone shape. And last thing, make a histogram or normal contour plot for the residual, right, to check the normality assumption. All right. Okay, so until now, we are done with all the steps of testing of the regression. All right, and then next, we want to talk about how good is the model, right? What we can say about this model, how we can decide whether this model is a good model or not a good model, or if I have another model, then how I can compare which one is a better one. All right, so the first thing we can decide is the R square. All right, okay, so as we said, R is the square of the correlation R, right? So we say when R square is close to 1, that means all the points will fall on the regression line. That means this regression line is good, right? This regression is accurate. The other way, if R square is closer to 0, that means there's no linear relationship between x and y, right? So that means our regression is not good at all, right? So this is the first thing we want to determine about the model is the R square. So we also call the R square is the coefficient of determination. All right, so this is the one we are familiar with, right? So the R squared represents the proportion or fraction of observed variation in y that is explained by the x. So this is the way how you interpret the R squared. The other thing we want to have to compare the models or determine whether this model is good is MSE, which is mean squared error. Right, so is this looks familiar to you? Still remember what is SE? The SE is root mean squared error, right? So actually the MSE, the mean square error, and the root mean square error, the MSE is just a squared SE. Right, so it's just under the square root part will be just a MSE. All right, so it will be just you have the once you have the residuals, and then you square every residual for every observation, right? So for our example, we have 52 stores, right? So that means you will have 52 y values. Based on the regression, you will have 52 predicted values, right? So here I can show you here, right? So we did the regression, right? And then again, let's come back to this output. Still remember this right triangle here? You will have so many options here, right? Okay, and then you will see that, okay, save predicts. So if we click this, what happened? When we check our original data, it will tell you what is the predicted value for each x. All right, so this column will be the observed y, right? So this will be y hat. All right, then I can ask the jump to show me something else to save the residuals. Alright, so you will have one more column will be called the residual cell. So what is this? Residual equals to y minus y hat. So which is, for this case, you will have 224 minus 288.87. You will have the corresponding residuals. Alright, so actually these are the residuals, and then if you go back to this output, right, so you will have what we want again, the residual squared, sum of the residual squared divided by n minus 2, right? So once you have the residuals, you can either use the Excel or click just create another column to be the squared residual, right? But actually you just don't need to do that step because MSE is shown in the ANOVA table, right? So which is mean squared error, so it will be this one. Or you can just square the root mean square error. Alright, okay, so you have many options to get the MSE. Alright, so what do we want for a good regression model? We want a larger R square. We want this mean squared error to be as small as possible. We do not want this random fluctuation, right? So we want the MSE to be smaller. All right, okay, so what is the relationship between these two? Still remember when we talk about the definition of R square? This one? Right? Okay, so R squared shows the proportion of variation in Y can be accounted by the modeling, right? And the other part will be just caused by the random error. So actually, this is the R squared. This is the MSE, right? So that means we want the R squared as big as possible. The other way, the MSE will be smaller. All right, so we say a good regression model should have a high value of R squared that close to 1 and also have low values of MSE and root MSE, right? So these two are the same thing, right? Okay. And the last topic we'll cover in this video. So the last topic we will cover in this video will be get the confidence interval for Y hat. We want to know what is the range for the Y hat if we have the regression equation. But the problem is for Y hat, we know Y hat equals to B0 plus B1x, right? So it is, we say when x is given, then we can plug in the x value into this regression, and then you can have the predicted value of y, right? So this is one meaning of Y hat. It predicts an individual value of y when x is given by a specific value, right? So we say the Y hat is individual value of y. But it also have another meaning. Remember that we have the model y hat mu of y equals to beta 0 plus beta 1x, right? So we say we use Y hat to estimate the mu of y, right? So Y hat has another meaning. It estimates the mean value of y when given a x value. Alright, so this Y hat have these two different meanings. is either for the individual value of y, or it estimates the mean value of y. All right, now we want to get the confidence interval of y hat for each of these two meanings. All right, okay, so first we will talk about how to get the confidence interval for the estimated mean value of y for this meaning. All right, so actually the idea is the same. You use the estimate plus minus the critical value times the standard error. All right, so in this formula, what is y0 hat? Remember, when we talk about y hat, we always need to be given a x value, right? So that we can calculate the y hat, right? So here we just have a specific value of x0. Then the corresponding value of y hat will be just called y0 hat. So for example, in our study time and the exam score example, right? So we have y hat equals to 20 plus 2x. X is the study time, right? Y hat is the exam score, right? Okay, now if I gave you the Rx is 30, then you can make the prediction, or you can plug in the x value into this regression to get the y hat, right? So this y hat will equals to 20 plus 2 times 30, which is 80. So that means this 30 will be just our x0. And then when you plug in the value of x0, the corresponding y will be y0. All right, so this is about the y0 hat. You just plug in the x value into your regression, you will get the corresponding y hat, and then this y hat is based on the x0, so we call it is y0 hat. And then we'll have the t star, right? So the t star is the same. You go to the t table based on the degree of freedom, which is, for now, will be n minus 2, right? And then alpha over 2. Based on these two information, you can find the t star from t table. The last thing is the standard error of mu 0. All right, so standard error of mu 0 hat will be equals to square root of standard error b1 squared times x0 minus x bar squared plus this. All right, so let's figure out for each one. So what is this standard error of b1? Still remember how to find it? We have the output, right? We have the parameter estimates table. We have the first row is about beta 0. The next part is about beta 1. So you have the first estimate for beta 1, which is the b1. And then you have the standard error of b1, which is 21.01. So will be standard error of b1. Whatever you got here, you need to square it. All right, and then times what? Times the x0. Still remember what is x0? Is the value of x you specify before you compute the confidence interval, right? Minus the x bar. So what is x bar? X bar is the mean value of x. All right, so how you can get the mean value of x? So we say the price, this column is x, right? We want to get the summary statistics table about this variable. So we do the distribution, we choose this variable, and then we want to get the distribution of this variable. All right, and then we stack it. All right, so this table is called the summary statistics table. it will tell you all the information about this variable. All right, so what is the x bar? The x bar is the mean value of this variable, so which is 9.55. All right, so this is x bar, the mean value of x. So you get it from the summary statistics table. All right. The last part of this formula will be the SE squared divided by n. So how you can get this SE? Still remember what is SE? The SE is root mean square error in the output, right? So which is the root mean square error. So this is the SE, right? So which is 156.64. Right, so this is the root mean square error in the output. Right, so where to find n? It is the observations in the output. Right, so observations will be 52, then this is the n. Right, okay, so actually from this formula you can find all the information needed. And then what you need is just make the calculation. Right, so here we will require you to make the calculation, even though we can ask a jump to get this confidence interval. We will tell you how to make it, how to calculate this by jump in the later data analysis too, but for our exam we require you to calculate this. We need to make sure you understand where to find this information. If for any software they don't have this function, you need to know how to calculate this, right? Because not every software will have this function to tell you how to find this confidence interval. All right, so next one we'll talk about the next meaning about y hat, which is the predicted individual value of y. All right, so to make the difference, we just call this is the confidence interval for y hat. This is called the prediction interval for y hat. All right, so it is to predict individual value of y given the same x value. All right, so you will see there's no much difference between these two variables, right? Okay, so we still have this formula, but you will change the standard error of mu 0 hat to standard error of y 0 hat. All right, and then the standard error of y 0 hat will have the same thing for in this formula, but we will have an actual term of SE squared. Right, so SE will be the same as E here. We just have an actual error term because when you just make the single prediction, there will be a lot of more random fluctuation, random errors, right? Okay, so that means the standard error will become larger, right? Because there will be actual source of error due to the random variability. All right, okay, so the calculation will be very similar, but we'll have an actual term if you are making just a single prediction for y hat. All right, so here we just go through an example and then we'll be done with today's video. All right, so we still have this example, beer sales example. We'll have the summary statistics for x, summary statistics for y. All right, and then we will need the summary of fit table. We will need the parameter estimates table. All right, and then first we need to find the 95% confidence interval for the mean value of y when x equals to 10, right? Okay, so when we want to find the confidence interval for y hat, we always need to specify the x value first. So what is this 10? This 10 will be just a x0, the specific value you want to plug in into your regression, right? So if you want to get this confidence interval by the formula, you need to first find y0 hat, right? So we say this y0 hat is based on this x0, right? So you just plug in this 10 into the regression, right? And then what? And then you just calculate it, which is 285.9 cases for y0 hat. All right. And then next part, that's t star, right? So we need to combine the degree of freedom and alpha over 2 in the t table, right? So the degree of freedom is 50, alpha over 2 is 0.025, so your t star is 2009, right? So you have y0 hat, t star done. The last thing is the standard error of mu hat, mu0 hat, right? So what is that? It will be the square root of standard error of b1 squared. So here there is a mistake. This should be the standard error of b1 here. There's no square here, right? So this is the standard error of the b1. So this is your b1. Then the next one will be the standard error of b1, right? So it would be 21.01 squared, right? So it would be the parentheses here, right? 21.01 squared times the parentheses of x0 minus x bar squared, right? So what is x0 again? The specific x value, right? So it will be just a 10 minus the x bar. So x bar is the mean value of x, right? So how to find it? In the summary statistics table of x. So this is your x bar, right? Okay, so you just go to the output to find the x bar, which is 9.55. So you have 10 minus 9.55 squared for this part. And then the last part will be the SE squared divided by n. So what is SE? SE is called the root mean square error, right? So which is 156.61, right? So you have it squared divided by the sample size 52, and then you just calculate the whole thing here. You will have a confidence interval. And then the next thing we need to do is always to interpret the confidence interval, right? So we say we are 95% confident that the mean value of y when x equals to 10 is captured or contained in this interval. All right, so here you need to specify it is for the mean value of y. All right, okay. Next, we want to find the 95% prediction interval for the same price, right? So that means this is still your x0, right? So based on your x0, you have already calculated what is y0 hat, right? So your y0 hat is still 285.9 because your regression didn't change, right? And then you have the same t star, you have everything the same. We just have one more term for SE squared, right? And then you just calculate one more confidence interval for the prediction, right? Individual prediction. And then if you compare these two confidence interval, you will see this confidence interval is much larger than this confidence interval because because we are doing the interval for just one single observation, you will have a lot of more variations there, right? So that means your margin of error is larger. That means your confidence interval is wider, right? So the next, once we have the confidence interval, we will be able to interpret it, right? So now be careful, we are not interpret about the mean value of y. We are doing for the individual value, right? So we say we are 95% confident that the 12 packs cases sold in the 1 week with the price equals to 10 is captured between this and this. Alright, so what's the difference between these two, actually between these two interpretation? Right, so here that means you only have one individual, right? You only have one individual value, so that means for just a one observation, that's with x equals to 10. What is the predicted value of y? But for this confidence interval, that means for all observations with x equals to 10, what is the mean value of y hat? Alright, so this is the difference between these two confidence intervals. This one is only for one observation with the price equals to $10. And for this confidence interval means for all observations with x equals to 10, what is the mean value of y hat? Alright, so we are done with this video. In next video, we will talk about the final step of the simple linear regression, which is to how to validate the model. Alright, so see you in the next video.